Okay, so hello again. I sent you guys Thursday a survey to fill out, see how we can improve the course and if you have any feedback. And none of you submitted the survey, like no one, zero response. So, uh, so I just prepared the lecture as last time. Please fill out the survey so if I have any questions. Today we're gonna do our discussion the third topic, which is energy. Then we have momentum as the first topic, and then finally fluids. I'm deviating from the textbook for this one because I didn't like the way the textbook explained or introduced the idea of energy and work. So instead, I wrote detailed lecture notes, and I will upload it after class, so you can study from it, not from the textbook. If you, of course, you can read the textbook still, but I will be following my own notes. I will also upload the homework right after class. It's already written. And I am not sure yet if we're going to have a lab for energy or we're going to have a combined lab for both energy and momentum next week, because both are related. We can do a collision experiment to confirm both conservation of energy and conservation. So let's get started for today's lecture. This is lecture 7. Energy and work. So what we're discussing today is just a conceptual definition of energy, and we're discussing qualitatively what the basic model of energy is. We're going to go over what we're covering in the whole topic, but in the next lectures, we will have more details and equations. Today is just qualitative. So the outline is, first, we're going to recap what we had so far. Then we're going to discuss energy, qualitative overview. This will include forms of energy and systems and energy. What do we mean by a system? Then energy transformations within a system. Then energy transfer is different from energy transformation because it's in or out of a system. And finally, we will discuss the law of conservation of energy. These are all topics within this chapter. We're gonna go over them in details, but today it's just qualitative. So let's get started with our recap. So what's happening with this? So recap. So far, over the last 2 weeks, we have discussed kinematics and dynamics. Kinematics was just the study of motion without considering its cause. So we just study like acceleration, velocity, position, without caring how the system got to move in the first place. Then in dynamics, we studied the cause of this motion. We studied forces. And finally, this cause and effect relationship was captured in Newton's second law, which states that force causes acceleration and can be written mathematically as F equals ma. So we can summarize that kinematics, dynamics. Kinematics, you have things like position, time, velocity, acceleration. Then for dynamics, we have forces. And the cause and effect relationship between the two is Newton's second law, F equals ma. F is the cause, and A is the effect. Okay? And this is an important conceptual point because you can easily get lost in the equations without appreciating what the equation says. Like physics is not math. Every equation we write down has an interpretation. So the interpretation of Newton's second law is that forces cause motion. So in principle, that's all there is to classical mechanics, Newtonian mechanics. If you give me all the forces acting on the particles in the universe and the initial state of each particle, I can predict the fate of any system. Let the system be the whole universe if you want. But in practice, this is very difficult and almost impossible to do. So we find it helpful to combine certain quantities together and come up with different definitions to help us better understand the physics and also simplify complicated calculations. So, for example, we can combine position with force to define a quantity we're going to call work done in a system. Or we can combine mass and velocity, the vector, to define momentum, linear momentum. We can also combine mass and the speed of an object to define energy or kinetic energy in particular. Here. And so on. We can keep combining different quantities, and then each of those quantities will have a different physical depending on the context. Okay. So the goal of this chapter and the next one is to see how this combination process works and how we interpret each one. Okay. So this is just a motivation of the chapter. So let's get started with energy. So we all use the word energy in different contexts in everyday life. We use it to describe different stuff. We can use it to describe the energy of a place. Like some places have spiritual energy, some places have vibrant energy. You can describe a person by saying this person has an energetic personality, or if you have an exam, you may have energy drinks. But in scientific context, when we say energy, when energy is mentioned, usually we think more of electric energy, for example, that's used to run the lights, computers, or chemical energy that's used to heat our bodies. There are different forms of energy, and there is not really a general definition of what energy is. It's rather characterized by its many forms and the fact that it's conserved. So we will introduce some of those fundamental forms of energy and see how energy can be transformed from one form into another. Then we're going to see how energy is transferred in or out of a system. That's, of course, after we discuss what a system is. And then we will come up with the conservation law of energy in an isolated system. So let's start with forms of energy. So one of the most important forms of energy is kinetic energy. We denote it by the symbol K, and it's equal to half mv squared. M is the mass of the object moving, and v is the speed of that object. As you can see, if this object is heavy, then the kinetic energy is large, and if it's moving faster, its kinetic energy is getting higher and higher. You can also see that it's proportional to v squared, not v, so it doesn't care which direction you're moving at. It doesn't. It only cares about the magnitude of the object. We will see how we derive kinetic energy in next lectures, but today we're just given the formula without proof. And this is usually associated with something moving. Anything moving has kinetic energy. Okay. Then we have potential energy. Potential energies include gravitational potential energy, spring potential energy between molecules in an atom, between molecules in like on the molecular level. So we have gravitational potential energy. We denote that by U sub G. Our textbook uses PE for potential energy, but the symbol U is more standard and you can find it in many textbooks. So I will go with U. And the gravitational energy, M8, close to the Earth. M is the mass of the object. V is the acceleration of gravity, which has magnitude of 9.8 meters per second squared. And H is the height of the object from the ground. So, for example, if you have a ball on a hill, height H, this ball has mass M, then this ball has gravitational potential energy mgh. It's an energy associated with position. Then we have spring potential energy or elastic potential energy. Both terms are used. Spring potential energy. This is denoted U sub S, and it's equal to half K x squared. K is what we call the spring constant. It describes the stiffness of spring. If K is large, then this spring is hard to stretch or compress. And X is the magnitude of compression or stretching of the spring. Have a spring like that. Its equilibrium position is here. Okay, this is X equals 0. And then you stretch that string up to this point by a magnitude X. Then has potential energy coordinate half kx. And also, if you compress it, by an amount x, it has the same energy source, half kx squared. So that you see x is squared, so it doesn't care if it's compression or stretching, because the sign is squared. Then we have thermal energy. We denote that E sub thermal. And thermal energy is basically molecules jiggling around. So in a way, it's a combination of kinetic energies and potential energies of the molecules on the microscopic level. So fundamentally, it's not a new form of energy. It's related to the previous forms, but when we're describing stuff macroscopically, we treat it as different things. We treat it basically as um, like heat. When objects have different temperatures, thermal energy is transferred from hotter object to a colder object. Okay. Then we have many forms of energy. So I'm just taking. We have chemical energy, and chemical energy is basically you have electric force to the atoms, so they bond together. So this bonding between the atoms stores energy, and when this energy is broken, we can release that energy in any form. So basically, this stored energy is chemical energy in a way. And we have nuclear energy, which is the energy stored in the nucleus of an atom. It's huge energy. If you can break it, it's transcended to huge amounts of energy. You can also have solar energy, wind energy, you can have all sorts of energy. But what we're gonna care about this class, basically the first three, these are the most important. And sometimes we're gonna care about the thermal energy, but only when switching. So we will characterize thermal energy by how much work. So this is only when we have friction. Chemical energy and nuclear energy are out of the scope of this class, so we're not going to talk about them at all. I just mentioned them. Um, so yeah, now we move on to systems. So we now see that we have many forms of energy. So we will discuss this. I'm just setting up some definitions. So when we talk about equations, deriving formulas, everything will be explained to understand what we're talking about, because this is relevant for momentum as well. Understanding what a system is very important for both energy and momentum. Okay. So all these definitions. One. A system is basically a collection of interacting objects. This can be as simple as a particle moving one dimension, like a ball rolling the floor. If in this case it only has kinetic energy, energy of motion, velocity, and has speed and mass, so it has kinetic energy, and that would be it, a ball moving. And it can be as complex as a city. Each of us has total energy, and the collection of this energy is a total energy. Um, the moon Earth system is a system. Like the sun and the earth together make a system. A cup of coffee is a system with all the molecules in it moving around. You can even think about one molecule as making a system by itself. Um, And we associate with every system in nature a quantity we call the total energy level. Okay. So definition 2 is the total energy of a system. We denote that by the symbol E. And this is just the sum of all different kinds of energies in that system. So it is, let's say we have kinetic energy, we have spring, we have gravitational potential energy, we have spring potential energy, we have chemical energy, we have thermal energy, plus dot dot dot. So if we denote that schematically like this is the system, and it has different kinds of energy. It has kinetic energy, dot dot dot. Okay. An example of this would be like a moving car, for example, has kinetic energy, motion. It has chemical energy in its gasoline. It has thermal energy in its engine. As you can see, since this system has many different forms of energy, have what we call kinetic energy can be so within a system you can have energy. So energy transformations are happening only within the system. That's what we call um so let me write that down. Energy transformation happens within the system, which is different from energy transfer, because energy transfer is into system or out of it. Okay? So, but before discussing that, we first define the environment. So if we have, just imagine the system of coffee and after you hold it, you count the thing. Okay? So what happens if it's a hold? What happens exactly? The thermal energy. Yeah, go ahead. Yeah, exactly. So the thermal energy in the cup is transferred to the environment. Like you can measure the temperature of the surroundings of the cup at a low temperature. So the thermal energy of the cup transfers into the in the form of, and we have few ways to talk about this. First, or heat work done. Uh, Work done basically feeling for a system. And heat is the non-mechanical work of other objects to the movement happens. So to find the environment, to be able to talk about energy transfer, we need to talk about environment because energy is transferred from the system to the environment. So what's an environment? The environment is everything that is not the system, basically. So if we go back to this picture here, the environment is all of this outside. Which takes us to the energy transfer definition, which is just exchange of energy between system and environment. Energy transfer is exchange of energy between a system and its environment. Okay. As we said, this can happen in two ways: work or heat. Work is mechanical, which means just pushing or pulling on a system. And heat is non-mechanical. We will only discuss work this class. We will not discuss heat because this requires thermodynamics. So we only discuss work. So we can summarize what we have so far. This kind of picture. We have a system. We have energy, kinetic energy, potential energy, chemical energy. We have transformations of energy. And we have transfers of energy from the system to the environment in the form of work done for heat. Okay, and this is the environment. This is called the basic model of energy. Okay? So yeah, this is the basic model of energy. Work, what we care about, and work is the process of transferring energy into the system or out of the system by doing mechanical forces, like by pushing or pulling on. So let's take examples. See, I don't think we're going to make it to the law of conservation of energy today, but let's take some examples on what systems do or how energy is transferred. So let's take, for example, cart. Okay, a person is pushing on a cart. I don't know how to draw a person pushing, but let's try. Person is pushing on a cart. Okay, so the cart is moving with constant speed. This is the floor. So let's focus on the cart as our system, just the cart, and the environment will be everything else, the supermarket, the floor, everything else. So this cart has kinetic energy because it's moving. So the cart has kinetic energy. Okay. The person is pushing on the cart, transferring energy to the cart continuously, but the cart doesn't increase. It's moving only with constant speed. So where does this energy go? Any ideas? Right. So there is friction. So as the person is pushing on the cart, the person is losing energy, right? This energy is transferred to the cart, but the cart is opposed by friction. So friction is continuously removing the cart in the form of, right? So that's why the speed doesn't. Friction is giving energy, and another example would be um, a person carrying a briefcase upstairs. Same happy person. Okay, briefcase. Let's make this a briefcase. This is height 0. Here to here. The height is 8. Okay, up to this point. So let's assume the person started to rest. It's just standing still at the bottom of the stair, and then after arriving at the top of the stairs, stop. So what happened in this case? Yeah, exactly right. Um, so the person holds the briefcase upward, so he transfers some of his energy into the briefcase, and this energy is then stored uh, as gravitational potential energy in the ground person system. Okay, so now the energy is totally potential energy, gravitational potential energy. And by the way, the word potential energy doesn't mean that the energy is potentially there. It means that this energy has the potential to do work, but it is energy, actual energy. Okay. Um, so yeah, in this case, there is energy stored, and you can store energy on a in a spring if you push it, as we said. So you can transfer energy and store it, not just lose it as happened with the shopping cart. Okay. We have four minutes, and we have the law of conservation of energy. So let's touch on it briefly. So as we said, work is defined as the transfer of energy into or out of a system. So you do work on a system, energy changes. So we capture this idea mathematically as the change in energy is equal to the work done. As usual, the Greek letter delta means change. So delta E is the change in energy, which is the energy final minus energy initial equal W. This is an important equation that we will use a lot. So as you can see, the difference in energy between initial and final is equal to the work done. If there is no net work done on the system, we define this system as being isolated. There is no energy input from the outside. There is no energy going anywhere. So it's isolated. For isolated system, we have W equals 0, no work done. And we get energy final equal energy initial, which is the conservation law of energy. Energy initial, total energy initial, equal to the total energy final. Okay. Total energy initial is the sum of all energy that we said. So it's kinetic energy initial plus potential energy initial plus chemical energy plus thermal energy. And all of these energies can be transformed between or amongst each other. So kinetic energy can be transformed to potential energy as long as the sum of them. So you can start with 100 joules of kinetic energy and 0 potential energy. And at the end, you get 100 joules potential energy and 0 kinetic energy if the object stops or something. But the total energy is the same. So this is the law of conservation of energy. We will discuss it in more detail next time because we don't have enough time today. I will upload the lecture notes. Please fill out the survey. And I will see you guys next time. It's an announcement. By the way, it's anonymous, so don't worry. Huh? Oh, thank you. You can say that in the survey. I accept compliments. Thank you. Oh, I couldn't. You guys hear me during the lecture because I have the mic. Is anyone still on the Zoom?